let me make the introduction. So as you know, we are continuing strongly our Quantum Horizon Preparatory School, and Kadir Hoca gave an excellent lecture yesterday, and he will continue today with this lecture. Well, people are still coming, but they can catch up, I think, because we are already 5 minutes late. So maybe Kadir Hocam, whenever you like, we can start.
Thank you, Hocam. So I'm just sharing the screen.
Sure.
Can you see the screen?
Yes, I can see.
Okay. So basically, shall I start, Hocam? Shall I start?
Right. I mean, people are still coming, but we are already 5 minutes late, so let's continue.
Okay, sure. Yesterday, I just talked about the need for quantum key distribution or any other post-quantum cryptographic protocols. So what are the security threats for the public key crypto systems? And where are the quantum computers on this problem? And then what are the precautions that we can take? And quantum key distribution as a solution to this problem. So I just mentioned all these things. Today, I will talk about different types of protocols and their challenges, the existing challenges of establishing large area networks, quantum key distribution networks. And I will also talk about like this, some other challenges of building this kind of modules for and networks. So yesterday, I mentioned the prepare and measure protocols and entanglement-based protocols. There are advantages and disadvantages of these kind of protocols. So prepare and measure protocols, you know, in the papers, if you look at figures, there is Alice and then there's an arrow to Bob. So which means Alice is the transmitter, Bob is the receiver. In this configuration, we call the protocol as a prepare and measure protocol, which means Alice is preparing the states and Alice knows what she prepares, and then Bob measures the states, and then Bob measures what knows what he measured, and then that's how you establish key between Alice and Bob. So for entanglement-based protocols, there is a distributor, quantum key distributor in the center. We call usually Charlie because A, B, C, right? It has to be C. So Charlie is in between and then sends the entangled photons to two sites, Alice and Bob. Alice and Bob only measures, okay? They don't prepare and send anything. So they just measure and then do some key negotiation between them using a public channel. And then that's how they establish the key. And the security of the prepare and measure protocols is relied on the quantum bit error rate. When the bit error rate is elevated a certain amount, you know that there's an intruder in between, which means there's a third party in your system trying to get the code, get the key, and listen to you. So the most common example for prepare and measure protocol is the BB84 protocol. And most of the world is using this protocol for quantum key distribution because it's very simple. You don't even need actual entangled photons or single photons. You can just use some attenuated pulses where the pulse on average carries either no photons or predominantly one photon. And the probability of having more than one photon is very negligible. So then you assume that it is a single photon source, and then you use it for state preparation measurement. On the other hand, for the entanglement-based protocols, they usually rely on some other quantum mechanical principle for security of the channel. For example, ACAR91 protocol, you check the violation of Bell's inequality value. So this Bell value is supposed to be larger than 2. Then you know that there is no intruder and the state you measure is having the quantum correlations. If the S value, after this algorithm finding the correlations, you just calculate the S value. If it is less than 2, then you know that what you have is a classical physical properties rather than the quantum properties, because the quantum correlations are lost. Therefore, you cannot violate Bell's inequality. So you do the binary check of security by using the Bell's inequality. For the security level, I would say one does not have any advantage over the other one. So ideally, they are both, yesterday I talked about this collapse of the wave function. So basically you do a measurement and the wave function collapses. Instead of a probability wave, you just have a classical state. Therefore, both principles are can be simplified into collapse of the wave function upon measurement principle. But entanglement-based protocol has some other advantages compared to the prepare and measure protocols. You can do teleportation, entanglement swapping. You can use it for combining the stationary qubits at different locations by using the non-local properties of the entangled photons. You make a distributed computing as if they are in the same place. You have this kind of advantages. And you can also do really accurate clock synchronization if you have a quantum key distribution network using entangled photons, because the photons are born together. Their timing accuracy is usually sub femtosecond. In this case, you can just use this measurement correlations, cross-correlogram peaks position to take out the offset and do the clock synchronization. So even if all the quantum key or cryptographic measures are for no reason, which means the quantum computers cannot attack effectively, and we don't need alternative crypto systems, still these networks can be used for accurate clock synchronization. So they can still be useful in that sense. So that's why those efforts are not wasted. So if I have to just briefly summarize how the BB84 protocol works. So basically, Alice is the transmitter here. As I said, it's a prepare and measure protocol. Alice prepares both measures. Alice prepares four different, she has pulses in four different polarization, linear polarization. It can be vertical, horizontal, plus 45 and minus 45 degree photons. And for this, you need reference systems, right? You need to define the reference systems. For example, for this vertical and horizontal, you just use this orthogonal or rectilinear reference system. We call it basis. You use rectilinear basis. So, and then you call horizontal 0, vertical 1, okay? And then you have diagonal state. You just shift it minus 45 degree. Now you have this reference system, okay? And in this state, the horizontal, which means minus 45, is 0, and plus 45, or in that reference system, the vertical is 1, okay? So therefore, Alice needs 2 random bits per one state, okay? One bit is used for either rectilinear or diagonal, okay? You need to choose which one, which basis you will use for preparation. And then you use the second random bit for choosing whether it's a 0 or 1. Therefore, for one bit of photon or state preparation, Alice needs 2 random bits. And therefore, you can understand from this statement that, Alice needs a quantum random number generator or any other true random number generator to prepare the states, okay? On the other hand, for entanglement-based protocols, you don't need that, because the randomness already comes from the vacuum fluctuations, quantum vacuum fluctuations. You don't need to do anything about it. So, and then she just spends 2 bits of random bits for preparing the state, either in rectilinear or diagonal state as a 0 or 1. And then she just sends the photons, and then Bob needs a random number generator as well, right? Because he needs to decide which reference system he's going to do the measurement. Now, instead of using a random number generator to choose which basis sends the photon, instead he just puts a beam splitter. Beam splitter just it's a piece of glass, you can think of it, and then in between there is some specific material. It's half reflective, and when a photon comes, regardless of its polarization, 50% probability that it will go to this basis, and there is 50% probability that it will go to this basis, okay? Therefore, Bob does not require an active photon quantum random number generator. Instead, he can just use a beam splitter. Beam splitter is his random number generator here. Once he chooses the random basis, or the beam splitter chooses the basis, and then there are polarizing beam splitters, and now he's doing the polarization measurement, polarization analysis, depending on which path the photon goes. Let's say for this polarizing beam splitter, if it goes here, it is a 0. If it goes here, it is a 1. And by doing this, Bob also gets the measurement outcomes. And then from a classical channel, Alice and Bob, they both share the timings of for Alice preparation of the photons, for Bob measurement time of the photons, and then they do cross correlogram to identify which photon was which for Alice and Bob. And then once they define this, also share the basis information. And then they classify the measurements into two groups. The first group, Bob was lucky and he chose the same basis as Alice. Okay. And then the second group, Bob chose the wrong basis, and it's not the same basis as Alice prepared the photons. And then the ones that are the same, you can use them as a key. So now you have your sifted row key. Of course, there may be some bit error rate due to some turbulences in this channel, some unwanted polarization rotations throughout the optics, and all these causes some bit error rate. And then Bob just devotes certain percentage of the key, sends to Alice, and then she just checks what is the percentage of the error. From there, they determine what is the percentage of the error in this quantum key, and then they do some bit error correction, and after that, privacy amplification protocols, and then they have a shared key on Alice and Bob's side, and then they can use this for communication. And then they basically use some symmetric cryptographic protocol like AES protocol, advanced encryption standard, and then they just use this key for encrypted communication. That's how it works. For the entangled protocol, I will not go into detail. I can just tell you that, unlike BB84 protocol, in this protocol, do not require any quantum random number generator. So the randomness comes within. Because you prepare states horizontal, vertical, plus or minus vertical, horizontal. So then the chance that Alice gets a vertical photon, 50%. And the chance that Bob gets a horizontal photon, again, 50%. Everything is 50% in this case. And then they just use beam splitters to choose between the bases. Just like what Bob did in the receiving side for BB84 protocol. Now Alice is also in the measuring side. Since there is no preparation here, the preparation is done within the source. That's why they don't need a random number generator. The one advantage of entanglement protocol over the prepare and measure protocol is don't need to trust the source. The entangled photon source could be in the hands of the adversary, your enemy. Still, you don't trust your enemy. You just trust the quantum physical laws. You check the violation of Bell's inequality. If you violate, then you know that there is no listener intruder in the channel. If it is below 2, then there is something wrong. So you need to cancel the protocol because somebody is trying to listen. Therefore, you do not need to trust the source here. Is one big advantage. So we talked about like advantages and disadvantages of two classes of protocols. Of course, entanglement-based protocols are harder to implement due to the fact that you need to build an interferometer, a quantum interference setup. An entanglement setup is eventually a quantum interferometer. So to do that, you need to prepare
Kadir Hocam.
There's a connection problem with Kadir's side, so let's wait a couple of minutes.
It's encrypted really well, I guess. Okay, he completed.
Yes, in case of trouble, always reset. Yes, so let's see if he will be able to connect again.
I think my connection is lost. Can you hear me?
Welcome back. Yes, yeah, now we can.
I don't remember, Hocam, where did I lost connection?
It was there,
like
the previous
here,
one.
right?
No, one more.
Okay, then okay, that's good. Thank you, Hocam. Thank you, İnanç Hocam. Basically, we use the spontaneous parametric down conversion process for creating entangled photons. It is spontaneous because it's driven by the quantum vacuum fluctuations. It is parametric because the process is parametric, so the energy and momentum is conserved. And it is down conversion because higher energy photon is converted into two low energy photons. That's why it's a low conversion process. That's where the name is coming from. After this point, I will use the term SPDC instead of all this long term. So basically, I will be talking about the type 1 collinear geometry here, because that's what I use in the experimental setups. In this process, the energy has to be conserved, like any other process. There are 4 conservation laws. 2 of them are here, momentum or energy conservations. They determine lots of important parameters here. We have a blue photon, 405 nanometer blue photon, blue laser actually. And then once it's passed through the crystals, most of the photons remain unaffected and they just pass. But once in a while, and the ratio is 10 to minus 11, which means 10 to the power of 11 photon passes by and just one of them interacts with the crystal. And then the blue photon is converted into 2 red photons where their energy is conserved. You can just put H bar in the beginning and then you can have the energy conservation here. Photon energy is equal to the signal's energy plus idler's energy. That's what we call them, signal and idler, the twin photons. And the momentum has to be conserved as well. Momentum of the incoming photon should be the same as the signal and idler photon's momentum. But remember that, this is like just collinear geometry. But it can also form a triangle like this. Like it can be like this. Okay, so in this case, you have the outgoing photons like this, and because of the cylindrical symmetry, you will see this circular shape. Okay, so BBO crystal is just looks like a piece of glass, but the cut angle is very important here. You need to determine or calculate using the Salmeyer equation. You need to calculate what is the cut angle for your crystal for the phase matching condition. Phase matching comes from the momentum conservation, and the momentum conservation dictates that what are the what crystal angle, what are the signal and idler wavelengths. Of course, energy conservation also tells you that. The photon energy, instead of this omega, you can just write C over lambda. And if you cancel the C's, you will see that in the energy conservation equation, 1 over lambda pump is equal to 1 over lambda signal plus 1 over lambda I. So that's how you can find the correlation between the wavelengths. So for this experiment, we use 405 nanometer pump light, and 780 nanometer and 840 nanometer photons comes out. And then once you put a filter, a long pass filter, blue photons will be, blue light will be cancelled. You will only be dealing with the SPDC photons. Of course, this is one way of doing this. The one that I explained is the critical phase matching. Okay, there are 2 types of phase matching in SPDC process. One is critical, the other one is non-critical. Third critical comes from the fact that the pump laser's angle with respect to the normal of the surface, crystal surface, should be fixed and really like fine-tuned. It has a little bit angle, suddenly the wavelengths is going to be different. And if the wavelengths are different, you won't be able to have this quantum interference because it is a phase-sensitive setup, and you will see that your fidelity is going down. So this is a measurement that I did in, I think, 2014 or something. So I just had an entangled photon source that was having fidelity of, I don't know, 90. This is visibility, so fidelity would be 0.95 or something like that. So not so bad for QKD. So then once you, visibility can be converted to fidelity, by the way, that's why it's the same thing. So once you tune the angle of the crystal a little bit, I'm just tuning the BVO crystal's angle, and then you see that the black one, visibility starts going down. I think around like 0.81 or something, it will stop violating Bell's inequality. Okay, and after that, everything turns in the classical regime. Basically, as you see here, you have a little bit of angle tuning range. So above plus minus 100 microradians, you will lose some fidelity in your setup. That's why if you prepare an entangled photon source, you need to make sure that nothing vibrates, and with the thermal fluctuations, nothing changes angle and all these things. You need to pay attention to these things. You cannot just put components and expect miraculously a stable entangled photon source. It will not happen, I can tell you that. So you need to stabilize everything. Even if you don't actively stabilize, passive stability of the setup should be there. So for this, in the quantum optics labs, you have temperature stabilized environment. You have some temperature locking scheme, and then the vibrations of the optical table are isolated. So you have an isolated optical table. So therefore, in the optical table, it's not a big deal. It's no problem. But if you want to prepare some source and then put in a satellite, and during the launch of the rocket, it shakes a lot. And then the angle should not shake, because this 100 microradians is a very, very small angle. So it should be very critical. That's why it's called critical phase matching. Alternative method is, you just have a periodically poled crystals. Instead of having this angle, you just have C-cut, and then you have this, do this periodic polling, up, down, up, down, up, down. And the polling period is usually a couple of micron. And then you send the pump laser to this crystal, periodically poled crystal. The angle does not matter so much. It does not change the wavelengths, output wavelengths. Therefore, you can still have entanglement. But what matters is the temperature. So in this case, the temperature is very, very critical. They are called periodically poled crystals. Most common example is PPKTP, PPLN. There are lots of other crystals, but the most common one is the PPKTP. In fact, the periodically poled crystals gives much higher number of entangled photon pairs per second. So their brightness is much better. But in our case, we don't prefer it for one reason, because we want to work with CubeSats or satellites. And in the satellite, you cannot control the temperature effectively. And the reason for that is, in the lab, how do we control the temperature? We just have a Peltier element. And the Peltier element, you can also call it a thermoelectric cooler. There are two plates. One plate is getting hot, the other one is getting cold. If you want to cool down, you need to dissipate the energy of the other side so that effectively you cool down the system. And to dissipate the energy on the hot side, what you do is you put a heat sink, which means a large surface area metal, usually aluminum or copper, so that the atmospheric molecules, gas molecules, keep hitting them and then taking the energy out of this metal. That's why you want to increase the surface area of the metal. And then you can do this because there is atmospheric pressure, right? There are some gases. But when you go to the space, in the low Earth orbit, the pressure is around 10 to the minus 7 millibar, which means you have high vacuum. And there, you cannot use this method for temperature using the thermoelectric cooler. What you need to do is you need to dissipate the energy by using radiative dissipation, which means you need to make a big metal dish to radiate the energy, and it's not very efficient. There are lots of experiments that was done in the Soviet times in the space, and none of them are really efficient. If you really have a really small thermal mass that you need to dissipate the energy, you can put a large thermal mass and then somehow solve your problem. But in this case, you want to control the temperature of a large bulky crystal. That doesn't work. That is why for space application, we usually use critically phase matched crystals, beta barium boron crystals. So these critically phase matching crystals, they are usually like older technology. The new technology is the non-critical phase matching. You control the temperature, and then as you see here, change the temperature here on this axis. Wavelengths are also changing and significant. That's why usually you need to control the temperature with 0.01 degree accuracy. That is quite sensitive. Okay, so it's possible to do in the lab, but if you want to put some platform, some fire and forget platform, it's problematic, still possible. But if you go to space, then it becomes almost impossible. You really need large radiative dishes. Okay, so these are some of the concerns. Of course, there are other concerns. So for example, every component that you have should be stable. Shouldn't be any yaw or pitch. The angle changes on any components. If anything changes, you will lose either brightness or fidelity. Something will be gone. Everything should be stable, really, really stable. To do that, you may need some really flexible metal components, at the same time very rigid. So I will talk about some tricks about that later on. So this is a typical setup for violating Bell's inequality we put in the space experimental setup. As you see, there are lots of components. So it's not easy to do the entanglement, because as I said, just think of a Mach-Zehnder or Michelson interferometer. They are very, very sensitive, right? You touch anything on the optical table, it's gone. This has double sensitivity because of the quantum interference, and therefore you have to be really careful about everything you put there. So you have a laser diode here. There are some components I will not go into detail. You have a half-wave plate here. Number 4 is, I think, half-wave plate. You changed the polarization of the light, pump light, into 45-degree linear polarization. You want 45-degree because you want horizontal and vertical components of the light to interact with the orthogonally oriented BBO crystals here. Half of the laser power is going to interact with one crystal, half of the power is going to interact with the other crystal. And you have HH plus VV photons here, still classical and separable state. And then you have some pre-compensator, spatial compensator 1, spatial compensator 2, and post-compensator 4 compensation crystals. And then you just fine-tune the angles of them such that all the distinguishable features of the horizontal and vertical photons are erased. And then you have an entangled state after the number, the 12th crystal here, which is a YVO crystal. And then you just put a diaphragm mirror to separate the signal and idler. You can do this because you use non-degenerate wavelengths. Non-degenerate signal and idler wavelengths are not the same, they are different. 780 nanometer signal photons goes this path, reflected, and 842 nanometer idler photons going this path. Then you just look at polarizations of these photons, do some polarization analysis, and you can violate the inequality. By the way, the number 15 here is crystal L polarizers, because polarizers, we just rotate them by hand in the lab. But if you want to do this experiment in space, you cannot change the polarization by hand. You can put a step motor to rotate it, but that is not efficient because step motor does not have high accuracy and it has hysteresis. Instead, we just use liquid crystals as the polarizers, linear polarizers, which works pretty fine. And the liquid crystal was used for the first time in this experiment, actually, in a quantum setup. And now they are like standard components for QKD setups for space applications. And just apply some voltage. Depending on the voltage that you apply, the polarization angle of the liquid crystal is changing. You can use them as liquid crystal polarization rotators. So now these are the techniques for creating entangled photons. Let's see who is doing what in the world. I think yesterday I mentioned briefly. Most of the world is, as you see here, using BB84 protocol. And these fiber networks, none of them is using entanglement-based protocol. BBM922 is still the same thing as BB84, but you just use actual single photons rather than weak coherent pulses. And there are some other protocols, but the most important ones, I would say, these three. As you see here, none of them is using a CAR91 protocol or any entanglement in these protocols. I don't know if it is here, but in MIT Boston, there is one network just using time bin entanglement, which is a form of entanglement. That is the only one that I know of that they are using entangled photons. So fiber is one mediator for transferring the photons from one location to another location with known losses, or losses inside the fibers. And another method is using free space, the atmosphere, to transfer the photons. But there is one problem here. Let's say this is the shape of the Earth. And, you know, if you want to send photons from here to here, because of the shape of the Earth, either you need to dig a tunnel or you need to go high altitude such that you can have a direct line of sight access. That is why this experiment was done in Canary Islands, and they did it in 144 kilometers distance. And the fundamental limit, considering the losses for free space, is pretty much 100 kilometers, practical limit, I would say. Same for fiber. So after 100 kilometers, the practical key rates are not achieved with the fiber networks. But the nice thing about this experiment was done in 2007 is going high altitudes helped solving the problem. Therefore, why don't we go even higher? Because if you look at the shape of the Earth here, I don't know if you can follow my mouse, but if you follow the shape of the Earth, only 12 kilometers from the Earth has a thick atmosphere. After 12 kilometers, it's vacuum starts, and then as you go even further, higher altitude, it becomes high vacuum. Therefore, there are almost no losses. For the losses in satellite-based experiments are much lower compared to the free space or fiber network. to give an idea how much is the loss. If you want to have a quantum network in Turkey from Istanbul to Ankara, which is around 400 kilometers, and if you use really nice fibers, this is a fiber that you can find in Oslo. It's 0.2 dB per kilometer. Okay, this is a good fiber, by the way, which means half of the photons are lost in 3 kilometers. And if you do the calculation for 400 kilometers, it means 80 dB loss, which means 1 out of 100 million photons will reach Ankara. So you send 100 million photons, only one of the photons reaches Ankara. So that's not practical, of course. As I said, after 100 years, the practical values are lost. For free space, it is less. The loss is less if you have to compare with this one, fiber loss. It's 0.07 kilometer dB. But the problem is this is very good weather. If there are some other weather conditions like windy or something, some turbulences, of course, your polarizations are rotated. There are some other losses. Therefore, I would say, considering all the other losses, on average, I would say fiber and free space losses are pretty much the same. But as you see here, for 100 kilometer realistic limit in this experiment, 144 kilometers in Canary Islands, they achieved 12.8 bits per second. Imagine in 1 second, you're only getting 13 bits of quantum key. It's extremely low. This is only 144 kilometers, just remember that. And then let's go to space. And for MICE satellite experiment, and the one that we did also in 2016, so the low Earth orbit altitude is 500 kilometers. 500 kilometers link, you send the photons, and the loss is around -35 to -40 dB, which means if you send 1 million photons, only 100 of them will reach to the optical ground station on Earth. This value is pretty good, actually, compared to this, 100 million, you send 100 million, only one of them reaches Ankara. 100 kilometers, only 12 or 13 key bits per second. You just compare this with the losses of the satellite, experiment. From 500 kilometers, you only have -40 dB maximum, which is if you send 1 million photon, 100 of them will reach the optical ground station. That is pretty good, actually. You can have some practical applications. So, and another thing is, it doesn't matter whether you're sending here or like vertical, it doesn't matter so much. Basically, as long as you're in the low Earth orbit, you can have a large coverage area. Therefore, satellite is a better option for having large area quantum networks. So the idea is having the CubeSats, because if you want to make something like the MICE satellite, which was hundreds of $millions, you cannot make another one. So even if you make another one, it doesn't even make sense. The problem with that is it's not iterative. So normally, the satellite industry is like this. You have a mission, you want to do something, and then you need to make a dedicated satellite that can do that can provide certain physical needs of the payload. But for CubeSat, it has very nice standards. Okay, you don't need to design specifically for anything. You just decide how many U you need. One U is 10 centimeter by 10 centimeter by 10 centimeter. You just put your payload inside, and like the power system, ADCS, attitude determination and control system, communication system, everything. The pinch antenna. Everything is inside, and then just like building Legos, you can make your own satellite, and it's very cost effective, very cheap. Even the launch of this satellite is very cheap. The CubeSats, you can usually send to like $100,000 to $150,000 for one Cube satellite. On the other hand, for large satellites, you need to have a dedicated rocket launch. So therefore, totally different cost. And if you manage to make everything miniaturized and fit everything inside the CubeSat, therefore you can have an iterative approach. You can send hundreds of them, just like Starlink. Starlink, right? There are 2,400 satellites, Cube satellites in the Starlink network. We can do something like that for the quantum as well, because it's very cheap and cost-effective and iterative approach. So that was the first experiment in space, actually, the SPEX-1 QKD precursor. What we did is we just wanted to see the polarization correlations inside the satellite, but there was no optical downlink. We just did all the experiments, entangled photon source, detection modules, everything is inside the satellite. We just did the experiment in space, see if we can preserve the entanglement properties there, and is there any fundamental limit? Because before we sent, we were keep getting the comment that I don't know about this field, but I was getting this comment in the conferences that because of the gravitational fields, we will lose entanglement. But we didn't see something like that. We definitely had pretty good entanglement, as good as we had in the lab. So this is how it looks like, the first version of specs, the entangled photon sources. So this black parts includes all the crystals, the ones that you see here. The setup is inside that black part. And these are high voltage amplifiers because you need high voltages for applying the reverse bias voltage to the avalanche photodiodes, photon detectors. And if you flip it upside down, this is the driving circuitry that we designed for running the experiments. As you see here, you cannot just say, well, I know physics and I know electronics and I don't care. You cannot do that. This is an interdisciplinary search and you have to work with the engineers to do these kind of things. And dimensions of this payload is, as you see here, there are 4 screw holes here. These are, like the satellite structure is there. There are 4 rods. You just put things inside and then you just screw them. That's how it works. And these dimensions are like, this is 9.4 centimeter and this 8.9 centimeter. The height is 2.4 centimeter, something like that. And the volume is less than 1 per 3 U. 1 U is 10 centimeter by 10 centimeter by 10 centimeter. So basically 1,000 cubic centimeters. And the weight was less than 300 grams, a can of Coke, And the power requirement was, by the way, this is inrush current. Inrush current means, there are certain times that, the experiment requires the most electrical power. We call them inrush current, the inrush power. In inrush times, the maximum power requirement is 2 watts. Therefore, actually, in the laboratory, when we want to do some experiments on these things, we were using this 9-volt remote control batteries for operating this payload. Its requirements are pretty low, actually. And then you need to do thermal testing, vacuum testing, vibration testing, because during the launch, the rocket shakes a lot. So then all these alignments, sensitive alignments inside this part, very solid and compact. That's why you need to make sure that you vibrate beforehand. And if any components is becoming loose or losing its alignments, you need to take precautions against that. And then there are radiations from sun, gamma and proton radiations are available in the, unfortunately, in the low Earth orbit. You need to do dose testing first, see if the electronics here, the chips, and even the crystals and avalanche photodiodes, everything is intact when there is this kind of radiations. So of course the radiations will kill them eventually, but we wanted to see how long would it take roughly. Like we don't want the whole payload to die in 6 months. Therefore you need to make some shields. For example, if you see this aluminum box, it doesn't only protect against light because it's lightweight. The photons cannot go inside. It is not only serving that purpose, it is also a shield, protecting all the components inside, APDs. These red wires are, and the yellow wires here are APDs. There are 4 APDs here, avalanche photodiodes, photon detectors. And their activity, it's a PN junction eventually. And if you have radiation on this one, the doping characteristics of the PN junction is changing. Therefore, you're losing your avalanche photodiode and it doesn't work like a photon detector anymore. So therefore, you need to make sure that everything works against this kind of radiation as well. So then these are the trials. The first one was a balloon test. So we went outside the atmosphere. And the balloon is a weather forecast balloon, hava durumu ölçme balonu. And it explodes in around like 30 to 40 kilometers. This one exploded in between. And we realized like in this explosion, what was the G and the payload survives, entanglement is preserved or not, these kind of things. And then we build a satellite, the one that you see on this picture. This is a 2U satellite. You see this is 1U and this is another U. Our payload is here. Okay, and there are some other modules to provide what this payload needs to do the experiment. And this 2U satellite was prepared by GomSpace, the company, the satellite company, the Danish company. We worked together to build the satellite and we put the payload inside. And in 2014, there was an explosion of NASA's rocket that was carrying our payload. Somehow, after the explosion, NASA found our payload and they said like the quantum unit looks like it's not affected that much by the explosion. How about you check it? And we realized that it actually works same as the laboratory reference measurements. Then, that was a good indicator that, if you do the engineering quantum engineering of the module really good, it can even survive the rocket explosion. Therefore, now the quantum experiments are ready to go outside the labs. The Galaxia was successful. It was the first quantum experiment in space. It was done in 2016. It is still orbiting, interestingly. It can fall down to Earth. We have the new one, I didn't indicate it here, spooky one, that was sent in 2020. I also contributed to that one. And that one just fell down after 6 months. But it finished the mission successfully. So this is the picture of the explosion. As you see, it's a giant, like massive explosion. It was really like a huge explosion. And as you see here, before and after test, it was almost unaffected, this explosion. So because you see like these crystals, you need to mount them really nicely with some components that, it's not too solid. If it is too solid, with the huge vibration, high G, high acceleration vibrations, you will just break the part. Whether it's metal or glass, doesn't matter. If it is too hard, it will break. If it is too soft, then it will just, like keep wobbling like this. And then eventually it may not stop in the initial location. It may have some hysteresis. You don't want that either. What you want is something really hard, but at the same time, really, really flexible. It can come back to original position. So of course, the main candidate for such a purpose is titanium. But the problem with the titanium is, when you machine titanium, the gels in the breakfast, gel, reçel gibi olur ya gel. So when you cut them with the knife, that after a while it just changes the shape. So that's called stress relief. So when you're cutting the material on the CNC machine, you're applying some stress. Therefore, you need to relieve that stress so that after when you send to satellite, it doesn't change its dimensions. And to do that stress relief process and artificial aging, you need to apply some heat treatment to the material that you put inside the satellite. But for titanium, even NASA did not provide a heat treatment profile. So when we go to the company for heat treatment, they didn't know how. So basically, by trial and error, we found our heat treatment for titanium. So even if I'm just a physicist, I did 6 months of pure metallurgical engineering to make these titanium pieces. And by the way, when we applied for patent for these titanium pieces as the mounts of these optical components, US Patent Office said this is too valuable and it doesn't make sense to get the patent of this. How about you make it a trade secret? The trade secret is something like Coca-Cola, you don't explain it, it's secret until somebody just finds the same method. If someone finds the same method, then it becomes serving as a patent. So that's why actually I cannot show these components and they're mostly covered in black. So there are details of like how do you mount these things and all the stuff, but you see some titanium components here. You see like white color components are actually titanium components to mount everything nicely such that even with huge vibrations, even if above 50 G vibrations, it's a rocket explosion, it's like a bomb, still, the dimensions do not change. So that was a really good engineering actually, but it was a good indicator that now the quantum experiments are ready to go outside the lab. This is just, like technical engineering side, but there's also quantum engineering side. For example, what is going to be the length of this crystal, BBO crystal? How long crystals will you put inside? You have limited space. Everything inside a CubeSat is really packed. So you want to put large, it's good because if you put larger crystal, one thing, the spectral limit of the signal photons becomes really narrow. And then the brightness, which is the number of entangled photon pairs per second, is really large for long crystals. Okay, therefore we should use long crystal, but how long? What is the optimized value for that, or where should we stop? So then what we did is like we just take like 15.7 millimeter BBO crystals, as you see here, and then formed an entangled photon source and did the coincidence measurements, and then look at the spectrum as well. And then what we have seen is totally surprising for us. I mean, instead of this green spectrum, we have seen the yellow one. It's really broad. And as you see here, 7.8 millimeter and 15.76 millimeter are almost having the same spectrum. So then it doesn't matter whether you use a long crystal or not. So we realized that after 6 millimeters, the spectral distribution is not getting changed so much. We wanted to understand why, because it's very counterintuitive. Nobody knows anything about this. So what we did is like we made some analysis, and eventually we realized that because of the birefringence of the nonlinear crystal, pump laser is having this Volkov. We call this Volkov. is coming normal to surface, and then because of the extraordinarily polarized, it's extraordinarily polarized with respect to the orientation of the crystal, it has some Volkov, and the Volkov, and it goes like this. And the SPDC photons are, when the Planck wavelength is having Volkov like this, they are created parallel to the crystal. Okay, so then what you have is you put some collection of some lenses for collecting them to the APDs, as you see here. Okay, the lenses here. So, but those lenses, certain collection of these, and the collection mode is well defined. And then once we look at overlap, actually you see this intersection area between the blue and red. We are only collecting from this volume. We are not collecting throughout the crystal, all the SPDC photon throughout the crystal. So therefore we realize that intersection of the collection mode and the pump mode determines what is the effective crystal length. It doesn't matter how long your crystal you put. And we realize that depending on our, of course, this depends on your collection optics, the lenses that you use. For our lenses, we cannot get any better than 6 millimeters. Therefore, it doesn't make sense for us to use any longer crystals. That's why we always use 6 mm crystals. So see, like you need to optimize this kind of thing. This is just one example. You need to optimize anything because there are not values that you can find in the books or papers that, you know, people tell you that, okay, use 6 mm crystals for satellite. This is the first time you're doing it. You need to determine all these problems. And, you know, look at the spectrum. I mean, if you have this green one, it would be nice. The yellow one, now you have more photons. There's always some trade-off about these kind of things. And yeah, another thing is, for example, do we want to use fiber in the satellite or not? Because fibers are known to have birefringence depending on the temperature drifts. And we know that if this is the Earth, you know, the sun is here, the satellite takes 90 minutes for the satellite to go around the Earth. So 45 minutes, it's getting fried under the sunlight, and there is no atmosphere to block direct sunlight. It's actually frying it. And then like 45 minutes eclipse, you're having cold temperature. Therefore, you keep having this hot, cold, this cycle 1.5 hours. Therefore, this birefringence will kill all the entanglement that you have in your setup. Therefore, we decided not to use fibers. But now the problem is we want as TM00 fundamental Gaussian mode photons as possible, because they are the one having the best fidelity. If you cannot collect a single mode fiber, most probably the ones that you cannot collect are not contributing to fidelity. So it's reducing the fidelity. That's why we want to use single mode fiber. But we decided not to use it. Then what do? We use pinhole in the confocal configuration to, you know, do spatial filtering. So you see, like, you need to do this kind of engineerings, the optical and quantum engineerings, to optimize everything that can work in space. So miniaturization itself is another trick, by the way. So if I have to give an example, I know that in DLR there is one CubeSat based QKD project. In UK there was one. Both of them are failed because this miniaturization itself is not an easy task. They think it's easy, but I can tell you that it's not easy. There's 5 years work of a large 21 people team to make this source. Now we have I have this know-how somehow. We can make it faster. You need to spend time and effort on this one, and I think this is the smart way to go, because IC satellite is hundreds of $millions, and later on I will show the, I think, market size. Look at it, the whole KD market is $0.3 billion. You already spent a fraction of it. One satellite is too much already. You don't want to send another one. It doesn't make sense because the QKD market is not a very large market, unlike what you think. Even the laser market is like, I don't know how many times of QKD market. So because it's a niche technology, so it will take time to, you know, have widespread effects. I think that yesterday, Cengiz Hocam asked a nice question about this. So anyways, I think that's why, like, miniaturizing the setup and using the CubeSat is more cost effective and smarter way of moving on, rather than just having a large satellite that carries almost 1 ton of payload. As if you send the optical laboratory to space. So of course, this one has the future because it's cost effective, very small amount of money. You can send hundreds of satellites like Starlink. So that's why it makes sense to miniaturize everything to put inside a satellite. So far, we put everything with discrete components, the bulky crystals and all these things. But the future is going to the silicon waveguide technologies or some integrated chip technologies. So basically, all these things that you see here all the components that you see here, you can do them by using some waveguides, okay? Some integrated chip. You can't do everything inside a chip. All the optics can be done inside the chip, but then the electronics is again bulky. You need to still miniaturize the electronics, but at least the chip part is promising for the future. I think the quantum technologies are evolving towards integrated chip studies. That's why if we have these integrated chips, of course, it's going to be even easier to design all these CubeSat compatible payloads for quantum experiments. So, for example, I'm sure some of you already know Mustafa Gündoğan, my friend. He's in Humboldt University. They are trying to make a quantum repeater out of BEC. So, and they want to do this again as miniaturized and compact as possible, because that is the future, and you can do this cost-effective and iterative approach to do lots of experiments in space. So about some of the experiments that we do in the campus, in the university, we have this quantum network. We are trying to have a quantum distributor and send the photons to the telescopes on the rooftops and establish a quantum key in between. So there, you can also do the same thing with the drones, but I must say that this is really challenging. I wasn't expecting it to be so hard. I think satellite technologies are much more mature than this technology, because drones are very, like, it's very hard to stabilize them. You know, the atmospheric turbulences, especially Çekmeköy wind, is awful. You know, you cannot lock the drone. So I think the satellites are much better for in this sense. But again, for different applications, drones might be used for as curious as quantum keys. Okay, so there is some pictures here. I think I missed that part. Okay, never mind. So basically, there are a couple of things missing for the space-based quantum applications. One of them is using a CubeSat to do downlink, sending the photons to two locations and distributing the key. That has not been done, and I know that two trials have failed so far. And I think, okay, personally, I try to do this business from the company side, industrial side, rather than the academic side. Because it's more like engineering, quantum engineering project rather than the fundamental physics. And the company Cubitrium, we are collaborating with Spectral, and I think Spectral is the only competitor to us in this field, CubeSat-based quantum experiments. And we have this Eureka project where we want to build this quantum modules that can operate in CubeSats, and we are basically making the modules. Sorry about it. So basically, we are making this miniaturized photon detectors and, you know, timestamp unit and the embedded system design. We are basically making all the hardwares, and this company, Spectral, is having this service providing business model. It's like GSM operators. You know, you want you know, internet, they sell you the internet, right? That megabits per second internet is that much liras, something like that. So they also want to do something like this. If you want quantum key, 1 gigabit of quantum key is $100,000 or something like that. I'm just making up the numbers. So they want to have this business providing, service providing business model. That's why they are not interested in the hardwares. And on the other side, we are interested in the hardwares. We want to make everything by ourselves to have this range of scale of products that people can buy and then build their own Legos and have their CubeSat-based quantum key distribution experiments. So other than that, you know, I would like to talk about the market sizes. So I said it's small, but it's smaller compared to the quantum computing market. It's not small at all, and it's, you see, it's also having this exponential increase. The market size is also having this increase for all these technologies. That's why I think for you young people, keep an eye on these technologies. If possible, have some learn something about this. If possible, go and learn from the people. I think you know, for me, education is only works one way. Usta çırak, you know, other way of education, I don't think it's very efficient for me. That's why, like, the best information, best know-how you can get is through someone who is experienced in this field. We really have good theoreticians and experimentalists in the country. So I know that there is a common trend of going abroad, but I can guarantee that, you know, you can find similar competitive researchers or such environments in Turkey as well. So just gain some experience first before thinking of going out somewhere else. And for this one, I think this field is really good and have a promise. If you look at the numbers, I will not go into details of them, but, you know, if you look at who is paying how much money on this one? As you see, North America, this is US, by the way, blue one. So this is the CubeSat technologies. As you see here, almost like all the CubeSat technology studies are done in US. And closer to Turkey, our geography, Israel is one of the biggest players in the CubeSat technologies. They are not spending so much money, but the novelty of the work they do is pretty good. And in the Europe, the biggest player is United Kingdom, UK. They're also spending lots of money. You see Russia here, but that's actually coming from this launching ramp and all these things. When you want to send a CubeSat from Baikonur or something, that's how this money is coming. I think it would be UK, Europe spending the most of the efforts for this CubeSat technologies. I will also tell you that, when you want to do something, keep in mind that, there are space applications and you need to be ready for these kind of tasks. And by saying that, I would like to finish my talk. And if you have any questions, I can try to answer. Thank you very much.
Thank you so much, Kadir Hocam. Do we have any questions in the chat? I can see one question from Buğra Yalçın, I think.
This is what I mean by trusted and not trusted nodes. I see. Okay. I just go to this slide. I need to share again. Do you see the screen? Can you see the screen?
Sure.
Okay. As you see here, like in this paper, the MySea Satellites first paper in 2018, see like one limitation of the current implementation of the QQD protocol is that you have to trust the satellite itself, which can be overcome in the future using a system. So the trusted node is like this. You have to trust this satellite, but they're not doing any tricks. Okay, so that's why China, if they want to provide service, just like what Spectral is aiming, if they want to provide service, and for example, from Turkey, we want to buy the quantum keys from this satellite, we have to trust them. On the other hand, if you use entanglement-based protocol, you don't need to trust the satellite because you will check the violation of inequality, and it doesn't matter if the source trying to play some tricks or not, because eventually you're checking it. So the trusted node means whether you trust this satellite as the mediator of the key or not. So if you don't trust it, so if you have to trust it, it's called a trusted node network. If it doesn't matter, even your enemy has the satellite, but still you're using the entangled photons, then you don't need to trust. In this case, it's not a trusted node network. That's how you differentiate between these two. Does that answer the question?
I have a little remark because Buğra said it is very clear. Nothing is very clear in science, yes. So you can ask what is the effect of gravity on entanglement, because on your pictures, these satellites are just stationary points, but it is known that if they move in their orbit, then their entanglement is also changing. So there is always some subtleties, especially gravity and entanglement connection is not very well understood.
True, Hocam. As I mentioned,
for small satellites, their inertia is very low. Yes, so this is also
true. And the altitude is changing, as you mentioned. So you're right. And we had this comment, especially theoreticians know this, spotted this for us, but we didn't see this actually in the low Earth orbit. Most probably the effect is too small to observe. We didn't see the effect of this one. If we see the effect of this one, I think we would publish a nice paper. It would be good for us, but we didn't see any effect of it yet.
Yeah, there are theoretical claims in 2000 since 2010s, but yeah, I agree there is no observation, but there is an open door of research there. Okay,
Yeah.
Thank you so much. So thank you,
Good job.
Inanç Hocam, also for waiting, and we can continue with Inanç Hocam. Maybe Ali Ikram Hocam will make the introduction and take the chairmanship here. Thank you so much, Kadir again.